Hello and welcome. In our last video, we looked at functions and their domains. And now what we're going to do is take a couple functions and then look at how we can combine them. So we can use algebraic operations to combine two functions. We can use addition, subtraction, multiplication, and division. And that may or may not affect the domain. Or we can use composition, where we actually apply one function to the output of another function. So let's take a look at the notes. And you can see we're going to just pretend that we have two functions, f and g, and just for the sake of making things easy to label, let's say that the domain of f is capital A and the domain of g is capital B. All right, so we can do a couple basic operations. We can add and subtract them, so that would be the sum of two functions. That's an easy way to combine functions. So if we were to write f plus g, for instance, that would be adding the functions together. And we would need to know what symbol we're using for the variable. So we might actually write this like f of g of x, so that you know x is being the input of the functions. And that's the same way of interpreting it as f of x plus g of x. All right, it's just a different notation. We could subtract two functions, and that would be looking at the difference of them, f minus g. So our notation f minus g of x is the same thing as taking f of x and then taking that result and subtracting the result of g of x. And of course, x is just any variable, so you could just as easily use s or t or whatever you wanted. Next operation is multiplication, taking the product of f and g together. And so a little shorthand notation is fg of x. And that just really means to take one function, f of x, and multiply it by another function, g of x. Now, before we get into quotient, one thing that all of these have in common is that they all would have the same domain. So f has a domain of A, and g has a domain of B. So you can imagine those sets of numbers are sort of like these circles here. Imagine that this is the domain of f. Okay, this is A. And then we have the domain of G, which is B. And all going well, there are going to be some values where A and B overlap. And these are numbers that are in the domain of F, but they're also in the domain of G. This overlapping area is called the intersection of two sets. The intersection of A and B. And a notation for that is A with this little cap B. And so that's just like the union symbol flipped upside down. And this is actually only the numbers that are in A and in B. Not just the numbers in either or, but they have to be in both sets. When you combine two functions together, you would better make sure that the value for x that you plug in is in the intersection of the two domains. The domain of these combined function are all A intersection B. So you can maybe find the domain of one function and find the domain of another function, but if you involve both those functions together, you have to restrict the domain to the numbers that are in both of the function's individual domains. Now, the next operation after that is the quotient rule. The quotient of two functions. We can take a function f and take a function g, and then we can divide them. So our shorthand notation f over g of x is the same thing as f of x divided by g of x. Now, the only difference with this, again, x has to be any number that is in the domain of f, but is also in the domain of g. However, you cannot choose values for x where g of x equals 0. So this is one little restriction here. In this case, the domain of f over g is still the intersection of a and b, but we have to also exclude any values of a intersection b where g of x equals 0. Okay, so we can look at a really basic example of two easy functions with very nice domains and combine them together and see what ends up happening. Okay, I've chosen two fairly basic functions. We've got f of x is equal to the square root of x, and g of x is equal to x minus 4. Now, if you were to think about the domain of f, we can only choose numbers for x that are greater than or equal to 0. So if you wanted to label the domain A in interval notation, it would be a hard bracket or a square bracket on 0 all the way up to infinity. X can be any number greater than or equal to 0. G of x, x minus 4, if you think about it, any number that is on the real number line, you can take and subtract 4 from. So in this case, if you want to call it B, B is all real numbers. So you can label that as negative infinity to infinity, or a symbol for the real number line, just in general, is R with a double bar. And now you want to maybe look at combining those functions. F plus g of x would just be the square root of x plus x minus 4. Now you might want to use brackets just to make sure that you've simplified properly, but in this case you can also just treat this without brackets as just equal to the square root of x plus x minus 4. Now, because I've combined the two functions together, and I still have a root x in there, this means I cannot choose values of x anywhere along the real number line. I have to choose values of x greater than or equal to 0. So the domain of this function, or the two functions added together, ends up being from 0 to infinity because f of x causes a restriction on the domain, even though b is all real numbers. And it's very similar for subtracting, but then of course you just have to be a little bit more careful about distributing a negative sign. So when you start subtracting functions, make sure that you may include some brackets in there and carry that negative sign through, so you end up with a negative x plus 4. And again, you cannot choose numbers that are negative, so the domain is from 0 to infinity. And very much the same if you're going to multiply functions. Using a bracket, root x times x minus 4. You could distribute that if you like, or you could leave it just as is. And again, you cannot choose values of x that are negative. Now for the trickier one. When we divide two functions, we have the same domain with an extra restriction that we cannot let the denominator equal 0. Now there's no way to really simplify this function in any useful way, so leave it as is. And you can see that the domain, we still cannot choose negative numbers because of the root x, but you can also not let x minus 4 equal 0. So that means x cannot equal 4. So this is the important piece down here that's a little different. X minus 4 cannot equal 0, which means that x cannot equal 4. So that means that the domain is all numbers greater than or equal to 0. We'll start at 0 with a round bracket, but it excludes 4. So that means we can only go up to 4 without including it. And then we'll start on the other side of 4 and continue to infinity. So it's just one little hole compared to the rest of these addition, subtraction, and multiplication operations. Now this will have great applications for things like if we look at profit, we define a profit function as being a revenue function minus a cost function. Profit equals revenue minus cost. So if we're given a revenue function and a cost function, then we can subtract these two to get the resulting profit function. Now there's one other kind of operation where we can combine two functions, and it's a little bit trickier. It's not an algebraic function in the sense that it's addition, subtraction, multiplication, or division. It's actually taking one function, finding the output, and then using that output as the input for another function. And that's called the composition of two functions. Okay, for the composition of two functions, we'll start off by assuming much the same thing as before. We're going to start with two functions, f and g. And if you want to, we can call the domain of f capital A and call the domain of g capital B. Now we have this notation. It's f with a little circle, g. Okay, it might look like fog, but it's not an O. It's just a very small open circle between the f and the g. Now, that is defined as f of g, where f of g of x is equal to f applied to g of x. So it's almost, you can think of that as just nested brackets. And so remembering that x is our input, the first thing that has to happen is g gets applied to it. So since g is the first function that we're looking at, we're going to look at taking something from the big set B here, which is the domain of g. We're going to pick a number out of that set, call it x, and that is going to go into our first function. And out the other side comes our new result, which is called g of x. And g of x is going to be a new value, and that value gets plugged into the function f. But the domain of f is a, so we'd better make sure that g of x is within the domain of f. So there's our second set of numbers or values, a, and we take this out of that set and we plug it into our next function. And once we plug g of x into our next function, we end up with f of g of x. So it's two operations being applied in a sequence. And so you can see there's a little bit of a restriction on the domain. We have to ensure that x is in the domain of g, and then our second requirement is that g of x must be in the domain of f. And if we don't have those two things satisfied, then f of g of x would be undefined. We need to make sure that both of those two requirements are satisfied. So we can go back and use the same example we just did, except that we can then look at f of g. Now we could also look at g of f of f, g of g. There's all kinds of different ways that we can use composition. And so if you wanted to reverse the order, g of f of x is just taking f of x, applying f first, and then take that result and then apply the function g. So it changes the order of the brackets. And it's just as okay to do f of f, a little bit weird looking, f of x. But what you do is you take the function f and you apply it to x, you get the result, and then you apply the function a second time. Same thing with g of g. And in fact, you can apply composition more than once. You can do f of g of f of g of h if you had a third function h. You just have to remember that you apply the first function, which is on the right, and then you apply the next function afterwards, which is on the left, and you continue in a sequence. So let's use the example that we looked at before. All right, we have the function f of x equals root x with the domain of all numbers greater than or equal to 0, and we have the function g of x, which is equal to x minus 4, and that is all real numbers for its domain. Now the first thing let's do is take a look at f of g of x. Okay, f of g of x is the same thing as writing f in brackets around g of x. So the first thing we'll look at is g of x. When you take x and you plug it into the function g, you get x minus 4. So this is the same thing as taking x minus 4 and applying f to it. Now, f, anytime you plug something into f, what you end up doing is you just take the square root of it. X is just sort of a placeholder. When we say that f of x is the root of x, that just means it's the square root of whatever you plug into it. So if we're plugging in x minus 4, that means take the square root of x minus 4. Now remember, for the domain, we can choose any number we like to plug in for x, as long as we're looking at the function g of x on its own. X minus 4 has a domain of all real numbers. But now that we've got the function f applied to that, we have to make sure that x minus 4 is greater than or equal to 0. So for the domain of this, the output of g of x, which is x minus 4, has to be in the domain of f, which is greater than or equal to 0. That means that x has to be greater than or equal to 4 now. So as an interval notation, we have a hard bracket from 4 to infinity, or a square bracket on the 4 and a round parenthesis on infinity. If we wanted to go in the opposite direction, we could do g of f of x. And remember, that means that we're going to take f of x first and then apply g to the result. Now, f of x will take x and then square root it, and g takes whatever input was given to it and subtracts 4 from it. So as a result, we get the square root of x minus 4. And make sure the minus 4 is not inside the square root, And sometimes it's a little bit easier if you put a little tail at the end of your square root so you make sure that the -4 doesn't accidentally get included. Now, what about the domain for this? You have to make sure that x is in the domain of f. So we know that we need to have x being greater than or equal to 0. And then we have to make sure that f of x is in the domain of g. But the domain of g is all real numbers. So that doesn't give us any additional restrictions on x. The only restriction was that x has to be greater than or equal to 0, or in interval notation, from 0 to infinity. Well, hopefully that gives you a little brief overview about how you can take multiple functions and combine them together. Sometimes the hardest part is trying to figure out the domain after you've combined them. Now we'll do some other examples in class, and this is going to be particularly useful when we look at things like the difference quotient in calculus. That's all for now. I'll see you in the next video.